This is our second video discussing applications of vectors. All the examples in this video will have to do with something that is on an inclined surface or a ramp and the force that it's required to keep it put. So we want to find the force required to keep a 3,000-pound car parked on a hill that makes an angle of 15 degrees with the horizontal. We'll round our answer to the nearest hundredth. Well, we know with all vector applications and trig applications, a good diagram is really important. So let's start with that. We have a car parked on a hill making 15 degrees with the horizontal. Here's our horizontal. And now we have an incline of 15 degrees and a car on top of it. Guess my car looks kind of like a spaceship. And it says that that car weighs 3,000 pounds. Well, remember what weight actually means. So the mass of an object is how much is actually there, but the weight of an object is the gravitational pull on the mass. That's why our weight is different on the moon than it is on the Earth, because of a different gravitational pull. So since weight has to do with gravity, our weight is always straight down, no matter whether we are on an incline or not. So I'm going to draw a vector representing this 3,000-pound car, and it's going to go straight down. And we're looking to find the force required to keep this car parked on the hill. Now, if you've ever pushed something up a hill or tried to keep it, you typically get down low when you push, and that's because you're trying to get your force to be parallel with the incline that you're on. So the force that we're looking for is a vector that is parallel to our incline. All right, the next thing I'm going to do is I'm going to create a vector that is perpendicular to our incline. And I'm going to have it start right here. And draw it down. And this is going to create a right angle right here. All right, so what I'm trying to find is the force, this blue vector. Remember that vectors can be moved around in the plane wherever we want. So I'm actually going to pick up that blue vector and I'm going to move it so that it connects the red and the green vector that I have drawn. I'm doing my best to make it look like it's parallel to that blue one. So this is actually what we're trying to find down here, our force X. Well, I definitely don't have enough information to do anything with this yet, so let's exploit our diagram. The blue incline and this blue vector here are parallel lines. I then have my green vector. That is going to be a transversal. So two parallel lines cut by a transversal. We know that alternate interior angles are congruent. So that means that we would have to have a right angle right here to match the other right angle that we had. Great. Also note, when I drew in that red vector, I told you that it was going perfectly straight down because that's how gravity works. And the original green line that I drew in here is the horizontal. So if my green line is perfectly horizontal and my red vector is perfectly vertical, that means that we have created a right angle right here. If I look at this little sub-triangle that's been created right here, I can find the third angle measure. I know that one's 90, one's 15, so that means that our third angle measure would have to be 75 degrees. Okay, back to our two parallel yellow lines. So those lines still parallel, and now we have a different transversal that's cutting. See, this red vector is also a transversal cutting two parallel lines, and alternate interior angles are congruent. Therefore, this angle down here is going to be 75 degrees. Let's take a look at this little subtriangle that's formed down here. I can find the third angle measure in that triangle. Again, we know they have to all add up to be 180 degrees. I got one that's 90, one that's 75. So that means that this one has to be 15 degrees. Now we have all of the information that we need to find x, but I'm going to draw a breakout triangle because this diagram is looking a little too complicated for me. So there's my red vector that measures 300. My right angle, angles of 75 degrees, 15 degrees, and what we're looking for is this bottom side x. If I use the 15 degrees as my reference angle, side x is opposite, and the 3000 is the hypotenuse, so I can just use SOHCAHTOA here. Sine of 15 degrees is going to be equal to x over 3000, and then we solve for x. Multiplying both sides by 3000, we get 3000 sine of 15 degrees is equal to x. And now all we need to do is plug that into our calculator and round to the nearest hundredth. The force that's required to keep this 3,000-pound car parked on a hill that makes a 15-degree angle with the horizontal will be 776.46, and our unit is pounds. The nice thing about all these ramp problems is the setup is really the same. I know when I was a student, I really struggled with the setup of the diagram. So make sure if you have any questions on that you're emailing me, because I've got a good grasp of it now, but that was always a tricky part for me when I was a student, and they are all exactly the same. So let's try another one. This time we have a force of 16 pounds required to hold a 40-pound lawnmower on an incline. What angle does the incline make with the horizontal? So in this example, they're asking us to figure out the angle of incline rather than the force required to keep it up. But really, the setup is exactly the same. So let's start with our diagram. First thing I'll draw is my horizontal. Then we have an incline of an unknown amount. We'll call this theta. A force of 16 pounds is required to hold a 40-pound lawnmower. So here's my lawnmower. I'm not even going to attempt to draw one. No, there's the handle. It's a 40-pound lawnmower, so that weight is the vector that is perfectly vertical. which then creates a 90-degree angle with the horizontal. And it says that the force required to hold it still is 16 degrees. So that vector is 16 pounds, 9 degrees. That vector is parallel with our incline. So we're going to move that blue vector to the bottom, to the end of the red one, just like we did in the previous example. So we're going to move it down here. And then we have our perpendicular vector that we drop from the incline down to this vector. I see I made my blue vector too long. So that's going to happen sometimes, but I like to see the right angle. So sometimes I'll draw in the one that is perpendicular to the incline, and then redraw this vector here on the bottom so that it, looks right. We're not doing proof by picture, but we all like it to look a little bit better. All right, so my incline and my vector down here are parallel. My red vector is a transversal, so we know that alternate interior angles are congruent. That means that this angle here, I guess I'll call it alpha, is going to be the same as this angle down here. Unlike the previous example, I don't know what that angle measure is because we don't know the incline of the angle of inclination for our incline. Okay. We also have our green vector, which is a transversal cutting our two parallel yellow lines, and alternate interior angles continue to be congruent, so that means that we have a right angle here. And then the last thing I need to label is I actually need to put the number on my blue vector down here at the bottom, right? That was 16. So we've got 16 right here. All right, so check this out. We know that these two angles are the same. They're both 90. We know that these two angles are both the same, alpha. Well, that then forces our incline angle to be the same as this angle up here. Because, I mean, there's only 3 angles in the triangle, and if 2 of them are the same, that forces the third one to be the same as well. So we can label this here theta. All right, I'm drawing a breakout triangle of the triangle that's down below. So we know this one's 40, 16 on the bottom, and what we're looking for is the angle of the incline, which is the same as this angle up top. And from our angle theta, we have the opposite side and the hypotenuse using SOHCAHTOA. That tells us that we're going to be using sine as our trig function. So sine of theta is equal to 16 over 40. You could simplify that fraction, but I wouldn't waste my time because we're just going to plug it into our calculator to figure out theta. If sine of theta is that fraction, then theta is going to be sine inverse of that fraction. And now we're going to plug it into our calculator and round to the nearest hundredth. We get theta to be 23.58 degrees. And that is our angle of inclination.